Welcome to the 16th Leonards lecture. And it's a pleasure and a privilege for me, especially, to introduce the 16th Leonards lecturer. This is Dr. Eduardo Alonso. He's a professor of geotechnical engineering at the, I'm going to say in Catalan, because now I can, Universitat Politècnica de Catalunya. That is the Technical University of Catalonia in Barcelona. He's been also taking some administrative responsibilities. He has been the vice rector for research at UPC. He received his bachelor's in civil engineering at the Universitat Politècnica de Madrid in Spain, which we share. It's both our alma mater. And his PhD at Northwestern University, so there is a little bit of a connection here with the Midwest. He has multiple research interests. He is well known for his work on unsaturated soil mechanics, but also he's one of these few individuals in our profession that I think has been able to bridge between soil mechanics and rock mechanics, and he's done significant work in tunneling and rock mechanics, but he also has interest in dam engineering, landslides. He has an extensive experience in practice in those. He has done theoretical work on thermo-hydromechanical and chemomechanical analysis. He's well known, his group is well known for the unsaturated soil mechanics software. He has published extensively. Last I checked, but may have been like a couple of years old, was listed at 400 technical publications, so maybe a few more now. He's the immediate past editor of Geotechnique. He's well respected in the profession. He has received numerous awards. He's a member of the Royal Academy of Engineering in Spain, the Royal Academy of Arts and Sciences in Barcelona. He has been given a number of distinguished lectures, the Coulomb, the Buchanan, the Sowers, the Crows, Heim, so on and so forth, ranking. We're going to have the privilege of having his ranking lecture also on Tuesday. Today is the Leonards. One of the topics that he's going to be talking about is kind of close to me. So we Catalans, we share something else. We are both Catalans. We've been trying to build this magnificent church, the Sagrada Familia, for more than 100 years. And there's been a lot of issues associated with that. The last one, and I think it's more political than technical, and probably will have the political discussions for the evening, right? That is going to the last one was that they had this high-speed train, the tunnel that was designed just next underneath the Sagrada Familia, and there was a lot of political clamor in Barcelona about the potential disaster of such a thing. But I think we were fortunate that Eduardo was part of the team of engineers who looked at that, and now everything is built and everything is nice and quiet. So Eduardo is going to talk about this project and others, share a little bit his experience in his wide and broad consulting experience, and he's going to talk about the protecting sensitive structures from tunneling in urban environments. So please join me in welcoming Dr. Eduardo Alonso for the 16th Leonards lecture.
Can you hear me? No? Yeah? It's okay. Thank you. Thank you very much, Antonio, for your very kind introduction. It's my pleasure to be here today. I would like to thank the Purdue Geotechnical Society and the university for this invitation. It's my pleasure. It's my honor, certainly, to deliver this 16th Leonards lecture. Now, well, I will talk about tunneling, and in particular in relation with sensitive structures. What I have in mind when I think in sensitive structures is this type of structure. This is the Sagrada Familia under construction. There are still, I think, 20 more years to go before completing it. Hopefully, we don't know. Yeah, this is the case of this controversy in Catalonia and in Barcelona, because this yellow line here along this Mallorca street was close to this facade of the Sagrada Familia, and this raised quite a bit of concern in the city. Now, if you look inside, this is the type of architecture that you have. So this is modernist architecture. And so it's complicated, in fact, to think how this will react against any soil deformation. But there are many examples. This is another one in Barcelona. Very recently, we crossed with a tunnel this Terminal 2 of the Barcelona airport. If you look around here, this is a delta area, very flat land and normally consolidated soils. And then the question is, well, there will be any damage here, how we can protect this building? This is something that I will try to discuss. Now, in this particular case, this is the situation. You see the tunnel is quite close to the structure of this is a cross-section of the Terminal 2. It's quite close to the structure. And you see the cover here, the cover to tunnel diameter, the cover ratio to tunnel diameter is close to 1 here. Is a little bit less than 2 in this in a section here. So these are situations in which you are concerned about the behavior of the structures. And well, in this particular case, just for you to have an idea of the soil, on the left you have the SPT, and in particular you see those 20 or 30, well, yeah, 25 meters or so of clay silt, very soft material. Well, this is the G value, which for very small stress, which increases as a function of course, of the confining stress. But here you have the undrained strength, and you see these correlations here, which actually are indicating normally consolidated materials. Those points, all of them, corresponds to pressure meter tests. Now, the cases that I will discuss were excavated using this machine, this type of machine, the earth pressure balancing machine, EPBS, and there are just a few, I think, main ideas to understand the work of these machines. The first one is that the tunnel itself, the dowels, are built inside under the protection of the shield, as indicated here. Now, the shield offers the reaction against the advancement of the entire machine. And then, of course, you have in the front, you have a rotating wheel, which is actually performing the excavation. And of course, there are more features here, but I will not discuss them anymore. Well, here is a photograph of the machine that is at present working in the airfield in the Barcelona International Airport. And you see here the jacks. Those are dowels just installed in place, and these are pushing forward the front part of the EPBS. Now, a very important aspect of these machines is the capability we have to control the pressures that machine can actually apply to the surrounding soil. And I indicated here 3 pressures. The one in the front, well, this is applied not only by the rotating wheel, but also by a chamber which is connected with the soil in the front part. And then you can actually control the pressure there. And this pressure, in general, this is a total pressure that is applied against the soil. Now, through the shield itself, not in all machines, but there is a possibility in some of these machines to apply also some pressure directly against the soil. But typically what you inject here in P2 is a bentonite. And the third one, which is probably the most important if you think in terms of any induced displacements around the tunnel, is P3, which is designed, in fact, to fill out this gap. There has been some presentation this morning. This gap that actually corresponds a little bit more to the thickness of the shield, which is, an important thickness. A few centimeters, 3, 4, 5, 6, 7, etc. Okay, now let me introduce something that all of you certainly will know. What are the basic ideas about deformations induced by tunneling? And this is an old work, but I will just review a couple of things here. Now, if you look at the surface and you look at the vertical displacements, well, what happens? You have a tunnel here. You are excavating. You have some so-called volume loss. Then the response at the surface is this smooth Gauss-like type of function that has this type of equation, which is an empirical proposal simply. Now, there are 2 parameters here. One is the maximum displacement, vertical, and the other one, this I, which is the abscissa of the point of inflection of this equation here. Now, another possibility of changing just the type of parameters you want to work with is to calculate the area of this trough here, and in fact then you get this expression here. Now you divide this volume loss by the volume per unit length excavated by the tunnel, so the area, the excavated area, then you have this Vs star, which is in percentage the volume loss. And then this is also an empirical relationship, which it works in many cases. So as a rough approximation, this I value here increases with the depth of the center of the tunnel in this manner here. So a very simple relationship here. Now, if you substitute here in this equation, now you have also this possibility of calculating, let's call the greenfield displacements, vertical displacements at the surface. You don't find here any parameter describing the soil, but there is this important parameter, which is the volume loss. And what is the order of magnitude of this volume loss? Well, I have indicated here 0.1%, small one, 0.5%, 1% in the past, much higher. But now we are able to work in the lower range. Now this is absolutely a key parameter in what I'm going to say. And the problem is that this parameter is essentially controlled by the workmanship and by the experience of the people actually handling the machine, which means that it's very difficult to calculate. Now, to complete the description of the surface, we have also horizontal displacements. But you can calculate them just if you accept that the displacement of the surface, in fact, is a vector that goes through the center of the circle, which is not exactly the case. In fact, it goes a little bit higher here, but more or less what I plotted here is what happens, and therefore it's just a matter of calculating this delta x horizontal displacement in a very easy manner. Now, if you have these two informations, the horizontal displacements that have this type of qualitative behavior, 0 here, maximum, and then 0, and the vertical one, then you are able to calculate those two ratios here. The first one is just the distortion, the deflection ratio. The second one is the horizontal strain. And those are the two strains that actually damage the building. And this damage has been characterized for a number of years already by very well-known contributions, such as this one by Boscardin and Cording, and others, using these two parameters here. This is empirical to a certain extent, but there is also some theory behind, in the sense that if you accept that your building is a thick beam, elastic, and then if you accept also that the damage appears when your tensile strain has some particular value, more or less 10 to the minus 4 means that the first crack appears, etc., and then you may increase that, then you get this type of relationship. Now, if you know this, then you enter here, and then you get a point here, and then you may have some estimate of what may happen when you build a tunnel. So far, I refer to so-called green field conditions. But the structures, of course, have their own resistance to deformation. And the next step was to introduce the interaction between the soil and the structure, representing the structure, this one, this building, again, as a thick, elastic beam. And this thick elastic beam has a reaction to deformations, which are controlled by this product of, in the case of horizontal strains, the modulus of the building times the area, cross-sectional area, and then for the bending moments, I being the moment of inertia. Now there is probably the first attempt to do that using finite elements and then performing a number of calculations by Potts and Addenbrook in 1996. And what they did was just to check how much the deflection ratios, for instance, or the horizontal strains were modified by the presence of the building. And they were modified in the good sense, because this ratio here is a number which is smaller than 1, and therefore the full problem, tunnel plus building, provides you, compared with the green field, a lower value. So that means less damage. This ratio depends on this ratio of, we may call it generalized stiffness of the building and of the soil in the manner indicated here. Now this was the case. It was later completed by a more sophisticated, well, in terms of geometry, I mean three-dimensional analysis. This is a more recent work. But essentially what all this is telling you is that your strains actually go towards the origin here, and therefore the building helps you. The problem, and you may be thinking that, is that the Sagrada Familia Basilica, well, to transform that into a thick beam is perhaps too much. And these are models that were built, in fact, to understand and to check the behavior of this monument against the tunneling. And this is the case for the crossing of the terminal number 2 in Barcelona. This is a complicated situation. It's a soft soil. We have seen that. The building is supported by piles of different lengths. And of course, you have a complicated structure here, etc. And then the soil. So you put everything together, and then you excavate. And this is the model that, in fact, there is people working with that, just trying to analyze the response. So very far away from this simplified analysis. So the situation is complex, and of course, you cannot never rely on calculations and on models. Professor Kreisig. And therefore, at the end, you have to protect the buildings. For instance, you see here how different is for instance, the settlements under this Terminal 2 compared with any simplified situation. This plot here shows you, with the scale of colors here, what are the vertical displacements under the buildings. All these are just the foundation plant in plan view of the building. So if you, in fact, make a cross-section here across here, this is what you get. So in red, you have the vertical displacements. In black here or blue, the horizontal displacements. Nothing to do with this nice Gauss equation, right? So this is so different. But is this correct? Well, as I said, I don't care at this. At this point, I would like to protect this, and this takes me to the contents of my presentation. So there are a number of techniques to protect the buildings, and I've mentioned here two, which are, well, relatively significant. One is compensation grouting. The other one is protection walls. I will mention another ones here at the end, and then I will also discuss some semi-analytical solutions that. Despite, our modern age and finite elements around, etc., complicated the constitutive equations, I think there is still some work to do, or we may gain something from using some analytical solutions, because they help to understand. And as a preliminary analysis, I think they're useful. In any case, I will show you what we have been doing quite recently. Now, I will start with compensation grouting. This is the Alcalá Gate in Madrid, and I bring this here because 3 years ago there was a tunnel actually being built just right here below this garden here, and this monument was protected by compensation grouting. Now, the idea is quite simple of the compensation grouting. So if the tunnel introduces some vertical displacements, then well, you try to counteract that by introducing some volume there that increases the volume around some particular points there, and then you compensate the displacements. And how do you do that? Well, the technique, I think, was probably put forward in France. In fact, this is a name that is well known, tube à manchette, and it simply means that the idea is to inject in a particular position. For instance, this position is along a boring. If you have a tube, a steel tube, and then you make a number of holes here in these particular positions, and you cover them with a rubber sleeve. This is a kind of a valve. It's a one-way valve. The the grout cannot come back if you inject it. And then how do you inject the grout? Well, you simply put a double packer in some particular position in which you have those holes protected by this tuba manchette. Then you inject, etc. And you can do that in different positions, different times. So you can do it many times until you get some volume increase. Now, the idea is just illustrated here. Of course, you increase the volume more and more. And of course, what you have to do is to check what is the reaction of the building and adjust your injection at the same time that you are looking at the response of the building. So in real time, you have to do that in real time. And this is the key component and the fundamental way of working of the compensation grouting, because nobody actually believes that you can predict anything here. Now, just to illustrate that, just the case, this corresponds to the Bilbao underground. Bilbao is a city in the north of Spain. Well, this is the situation. This is this slender building here, and a tunnel was actually being built, and not only a tunnel, but a station parallel to this facade of the building. The geology was quite complex, and well, the tunnel was relatively close to the foundation. This building was founded on isolated footings, and one end was on rock, which is not a very nice situation, but this was, in fact, the foundation of this building. So here is the station here, and well, you can see the complications here. In fact, this is a karst. This is a karst in these marls and limestones, and those are clays and gravel, which are the upper part. And so this is the building. So the idea was to drill these boreholes here in 3 layers here with this tuba manchette in order to protect and simply the building. Now, an additional problem here, but may happen in many other cases, is that the excavation of these underground stations and the tunnel itself created some, well, lowering of the water table. This, again, is a relatively common situation. So the lowering of the water table is indicated here. A number of meters, so from, I don't know, 68 or 60, yeah, 66 here to 80, so, well, 20 meters or so, and this is able to actually increase the displacements. And again, I mean, this is another source of displacements that you would like to compensate. And the way of doing that, this is a plan view, is, well, for some position, typically a well or some excavation that you have for some other reason, you may perforate a number of borings in the manner indicated here, and then you locate those tuba manchette. Each one of these circles here corresponds to a point in which you can inject, and then you simply follow the problem by looking at the building, by monitoring the building, and then by injecting. In this case, they did that in 3 layers of borings. The upper one, the blue, the red and the blue, they were injected in the first place just to create a kind of better conditions for the soil. And then the green one probably reacts in a better manner than the other 2. Well, this is at least the idea. Just this is a view of the works. You have the upper layer, the lower layer of the borings, and the center one. And of course, the building has to be monitored. And in this case, well, these are targets just to measure the 3 displacements. Just one result. Those are plots of displacements along time. And each one of them is located in a particular position of the building. And it reflects, in fact, the increase of the thickness of the soft soil under the foundation of this building. But what is interesting here is to realize that anything you do in these complicated situations, you know, with relatively soft soils, etc., has a reflection immediately into the behavior of the building. For instance, drilling starts. The only thing you do is to drill, but many holes. And then suddenly the building reacts with some settlement. And then some additional leak in the tunnel face. And then another reaction in the sense of an increased displacement. And then here the compensation grouting starts. Now, just the starting of the compensation grouting creates, again, some displacement, but they manage eventually to compensate that and then, well, to get some constant value. And when they accepted that, The building didn't experience much damage, and well, it's successful to a certain extent. This is just an indication, and you can, in the literature, you have many of these plots in which, just for you to have an idea what is the pressure that you apply in this case. Well, anything from, I don't know, something like 2 bars to 15 bars or so. And the diameters here corresponds to the volume injected. In this particular case, the total volume was around 100 cubic meters, not too much compared with other cases. But, well, this is just one example. This technique, I think, it started in Europe around 1990 or so. And it has been applied in many situations and in the big cities in Europe. I bring here only a couple of examples. One is the Big Ben in London, and this was the situation. So in the proximity of the Big Ben, they were excavating this, that's a called box, you know, with a well-braced structure here, and also 2 tunnels here, one on top of the other. And then they decided to compensate along this blue line here, which is located in London clay, which is a nice feature that they had this over-consolidated, quite homogeneous, very impervious tertiary clay. At on top, these are these gravels, etc. And then they control in a manner that I mentioned that is what you should do, your, in this case, inclinations. So you have some information here. In the lower part, you have the progress of the box excavations. So each one of these points in green corresponds to some work being done there. And here you have the construction of the tunnels. And then as soon as they started construction, they noticed something. Look at the scale here. These are millimeters divided by 55 meters. So it's a very small amount. But of course, we are, you know, very, very used to detect any change from verticality. So at some particular time, they started the grouting, and then, you know, you were fighting against the formations, and they were successful in doing that, and they stopped here. So they accepted these 20 millimeters divided by 55 meters, just a small inclination. But you know what happened later on? It continued for a number of months and years, in fact. Well, this can be explained. I mean, if you apply some increase in volume in a saturated clay, well, you will create excess pore pressure, etc. They will dissipate in time, and then something else will come later on. But apparently, it stopped here. So this was successful. And the second example, I will only show you this. This is a building in Amsterdam. I bring you this case because of the proximity of the pile foundations to the tunnel, and certainly to this compensation grouting boreholes here. They selected this silt, so a kind of a cohesive material close to, in order to apply the technique. Well, there is a lot of literature on this, but just very briefly, a comment on the deformation mechanisms. If you think in clays, the injection of a volume probably creates a crack, and the direction of the crack is perpendicular to the minor principal stress. So if you are in a normally consolidated cell, you could expect that initially the crack will be more or less vertical, and you don't like this too much, because what you want to have is some displacement in the vertical direction. But if you continue injecting in position 1, then the horizontal stress eventually will increase, and then it will become higher, and then you will change the direction of the minor principal stress. So with time, then your crash probably will be in the horizontal direction, and then you will push up the building. Of course, this is the case for over-consolidated clays. Now, sands are different, and the reason is that the grout, the typical grout, which is cement and water and something else, but cement and water, the water escapes because the sand has a high permeability, and then this grout becomes a thicker paste there, and then this space, the boundary of this space, migrates towards the origin of the volume increase, etc. You may force the situation, you know, increasing the pressure, etc. At the end, what you have is a volume increase. So for me, if I am thinking in modeling this at a big scale, the only thing that matters is that I have increased the volume in some particular points or region or area, right? Now, let me now introduce this idea of a semi-analytical solution in order to create some models that have some interest. It is unfortunate because I didn't arrive in time to bring here the application of what I'm going to say to a tunneling case, but it's close to it in some sense. But the idea, we are doing that. But OK, so what I'm going to tell you is in itself a different phenomena, but it relates to the increasing volume at some particular points below a foundation, a pile foundation, and see what happened. Now, this is a bridge in the high-speed line between Madrid and Barcelona. It's a 600 kilometers long line, but this is in Catalonia already. And these pillars are 50 meters high. And then, for reasons that I cannot explain here in detail, but this area here, this volume here, began to expand. Now, those pillars are 50 meters high, but the piles are 20 meters long. They are covered by a cap, which is very rigid, something like 4 meters or so of thickness of the slab. And the piles are 1.5 meters in diameter, so it's a big foundation. 3 by 3, so 9 piles for each one of these pillars. Now, they realized, the administration, the railway administration, over the years, that something was wrong because those pillars were going up. And if you look at the scale here, in a number of years, 5 years or so, they went up, well, something like 250 millimeters, 25 centimeters. The trains here run at a speed of around 300 kilometers an hour. So, of course, they were correcting that almost every day. But at some particular time, well, I became involved in this case, and so one of the first ideas was to locate marks, just to know a little bit more about this swelling, and what we got in a given time interval was this type of heave. So those are contours of equal heave in millimeters, and you know these are like ellipses, irregular ellipses, and the pillar is here. This is an interesting information, and I will tell you why. Now, this is now the problem. So I have some expansion zone. Well, it can be an expansion, or it can be a contraction, it can be anything that actually increases volume in any manner. This is the idea. And the problem is, and the question is, how a pile foundation will react when you expand an area here, in this case, below the tips of the piles, which happens typically in the buildings founded on piles in many cases when you apply compensation grouting. Oops. Now, so this is the theoretical problem. So you have your pile foundation with some loads on it, and then the key point here now is that you have, in this particular point, some increase in volume in some particular position. And how we can solve this? Well, in a simplified manner that uses fundamental solutions, you can do things like this. And this is, of course, well known. For instance, imagine that you think in terms of equilibrium, better than equilibrium, some compatibility of displacements in the horizontal direction. So you isolate the structure on one side, and on the other side the soil. Of course, this is approximate. But the only thing we are going to do is to, in each one of these particular points here in which you discretize your pile, the horizontal displacements. You can calculate this on the left. If you know this P with these forces, which you will calculate them using theories of structures. And on the right, you should use some theory that allows you to calculate displacements under this set of loadings plus this increase in volume. Now, the Mollet hypotheses, of course, are simple hypotheses, homogeneous isotropic soils, elastic response. And the third one, incompressible soil, well, these problems are kinematically controlled. So if you change the volume, I am going to say that almost irrespective of the constitutive equation of the soil around, this volume will propagate in a manner which is similar from one case to the other, which is a nice thing to apply these fundamental solutions. Now, what are the fundamental solutions that help to solve this problem? You know, Boussinesq, Milling in 36 derived closed form equations for the solution of a concentrated load inside the semi-half space. And then Sagaceta, he's my friend and my colleague. In fact, we did the career in Madrid together. He's now a full professor in Santander. And he published a very nice paper in Geotechnique in 1987, giving an analytical solution for the displacements in a half space when in any position you increase the volume by even amount. So it's a real fundamental solution. And so we did what I mentioned very briefly. So we created this model. And the first thing you have to do in these cases is just to check or to validate the model. And this information, the volume that you measure at the surface is very good to do that. This is kind of a green field type of information here. Now here you have a comparison. We didn't try to be very precise. We could arrange things, but okay, good enough. You can compare the blue with the black, and this is what we did. And then we apply that, of course, to the problem, which is what is the reaction of the pile foundation of one of those pillars. And here you have the calculated displacements. This is interesting because every pile has a different vertical displacement in this particular case. But if you look a little bit carefully to these blue bars here, you will realize that there is some symmetries there. And in fact, what happened with this pile foundation is that it tilted in a given direction. But this is a three-dimensional problem, right? And we were able to measure this tilt and to compare it with the calculation. And I was surprised that after all this and all the hypotheses, etc., you may compare the calculated inclination. So this is a tilt in two directions, x and y directions. This is in degrees, so this is a very small value again. This is the measured one in this particular time length. So, well, there are differences, but not that much. So the model was quite accurate. So it represented the problem. This is the point. Now, we are now to apply this. We are working on this because this is simple, and then it can help you, I think, to understand this problem. Now, let me move on to the protection walls, and I come back to the Sagrada Familia. So this is the tunnel. And these are the soils in the center part of Barcelona. We have a stiff tertiary sandy clays, these green and yellow materials here. And on top of that, there is a varying thickness of relatively old quaternary soils, unsaturated and also cemented, which is a good foundation in general. So the tunnel is relatively close to the surface. The problem is that on the surface we had this building. So the cover ratio again is 2:1 here. So after some thoughts, the idea was to protect the Sagrada Familia with a vertical wall. The wall was made of piles. Here are the characteristics of the piles. There are relatively long piles, 41 meters in length, 1.5 meters in diameter, with some gaps in between them. And the reason for that was to allow the water to go through, because there was there is a flow in Barcelona towards the sea. And on top, in order to fix this point, we also designed here this cross section here. This was just a big beam connected to the top of this pile wall. And well, this is the machine. A new machine, in fact, was used for this particular case. Is 11 meters in diameter. And this is what I was mentioning at the beginning, that is very important to control the performance of the machine by having information in real time from all the measurements at the surface. So you have a number of things that you can do. Most of them are pressures that you apply. Pressures that you apply on the front part, you can measure the weight of the soil being extracted, and also the pressures across through the shield, and also in the back part. You remember the P3, etc. And well, there was an office doing that, as I said, in real time. But now I would like to introduce again the value of some analytical thinking, just to understand a little bit more. What is the effect of locating a wall close to a tunnel? This is the problem. Of course, you can solve this using, I don't know, three-dimensional finite element, but this is not the point. The point is that I would like to go a little bit more, you know, in this simple way of thinking, but at the same time, I think is some value. So these are the hypotheses similar to the previous ones, but now we have different fundamental solutions that we have to use. The first one is Melan, which is equivalent to Milden, but now this is a line load. And the second one probably is not a fundamental as the others, but is good enough for my purposes. Now, this publication here provided a full representation of all the displacements around a tunnel based in part in the Sagaceta fundamental solution, but also introducing some real observations. But they were quite close in a number of cases to the actual measurements. Now, the idea is similar to the previous one. For instance, imagine that we want to find a way of solving this problem. Well, imagine, just have a look at the wall. Here is the wall, which is the key component here. You discretize it into a number of segments, not too many. I mean, any program that you later on build using these ideas run at in half a second. And on the right, you have the soil. Again, you have to, for instance, in the vertical direction, to make equal the displacements in the vertical direction. But in the second case, on top of the forces acting in this particular position, in which you have the discretized wall, you have the tunnel. And therefore, any displacements induced by the tunnel have to be introduced here now, the vertical ones. And of course, you have to ensure all the time equilibrium, okay? Total equilibrium. Oops. Sorry for that. Yeah, just for you to have an idea of how these fundamental solutions are in this particular case, this is the 1932 Melan equation. The only parameter of the soil here is this E, this modulus here. For the ground loss, which is the key component here, you will not find any reference to any soil property. These problems, as I said, are very much kinematically controlled, except, of course, for this ground loss. So anything related to the soil should be there. And in fact, this is the case. However, as I said before, the type of soil controls to a certain extent, but not too much. What is fundamental is how do you handle your machine. So, but this is nice, because this is what the people working in tunneling understand very well, what is the ground loss. And now this is what I said. So you have to impose these soil displacements in the wall and in the soil. In the soil, you have to take into account the presence of the tunnel, you ensure equilibrium, and then at the end, you have to solve a system of equations. And you do that, and then I'm going to show you some results. Now, a first advantage of doing that is that automatically, from this type of analysis, some dimensionless coefficients come in a natural way from your equations there. And those dimensionless coefficients control the problem. And in this case, those are the four that actually control the problem. The three first coefficients, pi 1, pi 2, pi 3, are related to geometry, so the position of the different elements there. And I've written here what are the usual values from the minimum to the maximum that you may find in practice. The fourth one is a stiffness ratio, as in the previous case. So this is the stiffness of the soil, this is the stiffness of the wall itself. And then let me show you some results with this particular analysis. Now, here you have what I call here a base case. So this is just a little bit randomly, not exactly, but we selected a given geometry and a given stiffness ratio. And what I represent here is the effect, which is very important, the effect of the length of the protecting wall. And if the length is 0, you have what we call the green field solution, which is just, in this case, this Gauss type of equation. But as soon as you increase the length of the wall, then in the protected area, which is from this point to the right, this is the protected area, then the settle must begin to decrease more and more and more as you increase the length of the wall, which is something that you could expect. And in fact, there is a way of showing that, is defining some efficiency coefficient, and this definition looks all right. So 0 for this eta means no effect, 1 full effect, so between 0 and 1. And then here is the effect of this length of the pile, of course dimensionless, when you increase it on the efficiency. And this is interesting, you know, beyond a certain length, you have an increase all the time in your efficiency, but then the rate of increase decreases. So, well, you may think that this is, I mean, you may select any point here, of course. If you are protecting the Sagrada Familia, you go deep. And this is what we did, because with piles of 41 meters. These calculations were made for just as an example, for a volume loss of 1%. And so here I introduce this fundamental information, 1%. Now, I can then check other aspects of the solution. For instance, the effect of wall stiffness. You may look at this effect here. Of course, when you increase the relative stiffness of the wall with respect to the soil, then the efficiency will increase, so you may go from the right to the left. But then, beyond some stiffness, the increase is almost 0. Again, this is a very nice information in order to design. This is difficult to get from finite elements unless you spend, you know, a lot of time and effort doing that. Now, the effect of the distance of the pile wall, it does not contribute too much, this distance. Of course, you have to locate that where you can, but it's also useful to know that if you make some, you know, changes there, this doesn't play much role. And we also were interested in checking this solution against a better solution. Well, better in the sense that you use, for instance, in numerical analysis. And if you have to compare elastic approaches, then imagine a finite element under elastic conditions. So this is the case of this comparison. This is not so easy to do immediately, because you have to check that, for instance, the volume loss or anything, I mean, may be used to select the same case. And in this particular case, what we did was to ensure that we reproduce the maximum settlement of the simplified procedure and the maximum settlement of the elastic solution. So just to have a reference which is common, which makes some sense. Now, what is interesting here at the very beginning is the green field solution for the two cases. In blue, you have the green field for the elastic means finite element elastic. And in green, you have the green field for the Longanazan and Poulos. There is a difference there. In fact, a fundamental difference. We know that if you perform an analysis using finite elements, unless you are careful and then you introduce, for instance, a small strain type of variation of the elastic modulus with a strain, unless you do that, your trough, your Gauss shape is very open, which is not the case in general. However, of course, Longanazan and Poulos, they use a much, better knowledge in the sense that we have accumulated already much information, and the green field is very much reduced. And this is the green part here. But we introduce that, of course, into the simplified analysis. Now, what you have here is now the effect of increasing the length of the wall. Well, you get things that are similar to my previous analysis. So we can now compare the two cases, the elastic finite elements, the simplified solution using fundamental solutions, and those are the two curves here. The blue one, which is the simplified analytical solution, the elastic, which is here in the lower part, this yellow curve here. There is a difference there. But I think it's better the blue one, because of this better adjustment of the green field case. And also I have represented here a recent work, relatively recent, by these two Italians, Pilota and Russo. There was a paper published in the Journal of the American Society. And well, they did quite a bit of elastoplastic finite element analysis. This range of values here corresponds to this particular lengths of the wall. They introduced also the soil stiffness increasing with depth. However, my criticism to this analysis is that the domain that they used was relatively small, and in particular the lower rigid part was relatively close to the tunnel, and probably explains why the efficiency is higher here. But well, this has to be checked in any case. But nevertheless, I mean, we are there, and this is the point. You know, with our fundamental solution, which are so simple, in fact. Now, let me just show you some additional information about the Sagrada Familia. Well, you have here the construction of the wall, very close to this facade here. And this is a case that we actually could transform into parameters, our dimensionless numbers. Here are the numbers for the Sagrada Familia. And then you might, well, try to apply this theory. Here it is. This is the previous base case that I more or less we invented. And then the Sagrada Familia case, this is the efficiency as a function of this stiffness ratio. We are here, this 0.006 is this value here, 0.006. And then if you go here to the right, to the efficiency, this is around 0.6, or so a little bit more. In terms of the length of the piles, we selected a length which is 8 times the radius, which is a depth of length of the piles of 40 meters. The efficiency is should be the same, something like 64, 65 here, 0.65. Is this a good information? Well, to a certain extent, because you have to multiply this by the greenfield settlement, how much it is at the design stage. It's very difficult to predict. And of course, since we don't rely on any method, then we have to check. And in this particular case, it was a massive use of many type of instruments just to detect any motion. Each one of these stars here in blue corresponds to a target in which you have 3 displacements. This is the Sagrada Familia, this is the building in front, and then, well, you can read this, and there are many other instruments here in order to have an idea of how this excavation performed. This is the Mallorca street, this is the position of the wall. You see the street is relatively narrow. Well, this is the so-called modernist quarter in Barcelona, so the streets were the streets that they were building in, I don't know, in 1910, 1920, around those times. So the tunnel was, fitting the street. And, well, just, the type of work that we had to do, to locate the targets, etc. And now the most interesting part, which are the measurements. Well, first, what was measured, really? This is the wall here. This is the protected area. This is 0. So no displacements in the protected part of the building. A little bit of displacements in the street itself. How much? Well, look at the scale here. This is 1 millimeter, 2 millimeters, 2 millimeters. If you compute this area here, is 0.04%, a small amount. Now, those are the calculations, the best ones that were done before actually measuring it. You had to make some hypotheses. 0.5%. I mean, this is typically we said today. In other projects, we don't go to more than 1%. 1%, yeah, I think that everybody could actually achieve that. So 0.5% means a reasonable excavation. And you see, what we calculate here is something like 6-7 millimeters or so compared with 1, and also some displacements in the protected area, 2-3 millimeters, which is not too much, but I mean, in fact, there was almost nothing. And then along the street, well, it was almost impossible to measure. 1 millimeter, 1.5, 0, nothing along the street. So the people criticizing so heavily our work here, when they knew this, they said nothing. And the journals in Barcelona said nothing. They didn't say, well done, no, never. Okay, so of course we took a number of precautions. You have to take care of the machine before entering in a critical part, and this was done by a number of shafts. Well, you have here some. Well, this is one. Well, here is the Sagrada Familia. So it's one of the points in which you stop there. You change all the cutting wheels, etc. at the front. This is a very interesting development This is like an earth pressure balance sheet, but going in the vertical direction. So this is a way of creating a huge well using a machine, which is similar to the one that you use for horizontal. And you see, again, narrow space, you know. This is an ancient quarter in the city. This is our red soil, and this is the Sagrada Familia, and these are the piles. And now I go to the final part now, which is going to be very brief. Other mitigation techniques. This is a beautiful picture of this Convento de Carmo in Lisbon. It has been left like that, just as a monument to the terrible 1755 earthquake that killed, an estimation of 100,000 people in Lisbon. But this monument was very close again to, because this is what happened in cities. I mean, the monuments, if you develop the city and you develop the metro, of course, you will find them in your excavations. Now, in the case of Lisbon, one of the techniques they use in the lower part, close to the river, to the Tajo River, was to improve the soil, using in this particular case jet grouting. So this is like an enclosure of jet grouting, and then you perform the tunneling here. I don't like these solutions too much, I must say that. Because the jet grouting itself, it creates an increase in volume, difficult to control in many cases. So, but this is what they did here. Now, coming to my case of the Terminal 2 in Barcelona, these are drawings taken from the project. The project was revised before actually entering into the Terminal 2. And I remember looking at this, so they asked for our opinion there, and I said, well, this kind of slab made of jet grouting, I don't see the value of this, you know. All this improved area here is within a volume that will go down because of the tunneling. So it doesn't have any possibility of supporting anything. So it was removed. So this is a mistake, in my opinion. And this is another mistake also. This was in the project also. So in order to protect this part of the Terminal 2, they decided to, this has been also used in other cases, but this so-called inverted tent using micropiles. So you look at this, and you say, well, where are those piles going? You know, this is the tunnel here, so they will move down. So what is the purpose of this? This was also removed from the project. And, but there are other cases in which you have to do something. And one technique, well, it's not a technique, but it's a way of protecting a building, which is more or less, I mean, almost unavoidable in some cases. This is a case in Lisbon again, but the tunnel was so close to this particular building that you have to do something because some motion is expected here. So in this case was just to create some transfer structure there just to support the building. This is another case which is interesting, again from our project. There is not my project, but the project that I criticize, in fact. You know, this was a solution proposed by structural engineers. They said, okay, this tunnel is relatively close to this foundation here, and then they said, okay, let's protect the building. And then they decided that the good idea was to introduce this structural reinforcement, you know, which is represented here in red. But you see, the two points here in which this is supported, this beam there, will go down. I mean, if you take it to the extreme here, to some fixed point here, or to some fixed point on the left, I can accept that it will do something. But like this again was removed. And then I come to the end. There is, I think, a very interesting procedure to control displacement, which is to act on the machine itself, and in particular to these three pressures, P1, P2, and P3 that I described previously. Now, our experience in Barcelona in the construction of the metro is that the volume loss is very much controlled by the pressures. By P1, I didn't introduce more details here. P1, P2, and P3. And in fact, when you increase them systematically, the volume loss decreases. And then you may say, okay, this is good, then this is the only thing we can do, or we may do, because this is simple, and then you avoid all complications. This is true. The problem is, there are two problems. One is that if you increase the frontal, this P1, then you may get close to blow-up conditions, and then to push it up the soil, which, well, is something that but this is, in my opinion, not so significant. The other one is that these machines are designed for some pressures and for some environment of working. And the experience is that if you increase those pressures, there's something begins to go wrong. For instance, I think there are some deformations inside. You cannot build so easily your tunnel, your dowels inside the protection of the shield, and there are internal difficulties to handle it. So you cannot increase this pressure, for free. So there are some range of pressure that you can use, in fact. But this is a very good idea. And then in the case of the crossing of the Terminal 2, so we decided to increase the pressure if compared with the previous excavation, in the fields coming to the airport. And well, the P1, we didn't want to change it. It was already 1.15. The horizontal stress, the total horizontal stress is the reference stress for P1. Yes, it's quite simple. This is the rule. So you might increase it, but we didn't increase it too much. Now P2 in this case was 0 because this machine didn't allow any injection through the shield. But P3, which is fundamental to avoid any deformations, because about 80% or so of the total displacement is controlled by this grouting here. And here we introduced an increase in pressure of 0.8 bars, which we compare with something like 2 point something is a significant increase. And now the results. Now, the best calculation using a complicated model validated in the greenfield part. And the model includes the structure, the soil in 3 dimensions, and of course the excavation of the tunnel is the green curve here. Now, the scale of displacements is on the right. And the red line are the measurements. You see, we went through the terminal with, I don't know, the maximum was around here, close to 5 millimeters, and then 2-3 millimeters, 0 here. Those are the cross sections, 1 and 2. The green is the calculated. The red is the actual measurements. Look at the scale here, a few millimeters here, almost nothing here, 2-3 millimeters. The same here for the profiles, 3 and 4, almost nothing here. Now the machine now is entering the airfield, but the aviation authorities have stopped the work because now we are entering into a high season in Barcelona, and so they have to use the different runways, so they don't want to see any machine working under the planes, landing in Barcelona. So I come to the end. Now, you remember at the beginning I was describing briefly those simplified procedures, which I think are useful for regular buildings. However, I think they are of limited interest in complicated buildings. And then, well, not of limited interest. The point is that a complicated building should be protected, because if you make some mistake, then you go into real trouble. And so compensation grouting is the first technique. My overall impression is that, well, I don't like it too much. Sometimes you have to use it. Difficult to control. I think there is a tendency to escape a little bit from compensation grouting. This is my feeling. But in general, in clay soils, you get better results. In sand, it's quite difficult. Now, protection walls, in my opinion, is a reliable procedure, but sometimes you cannot use it, because if you go under the buildings, you cannot use any protection wall. And the semi-analytical procedures, well, I like this way of approaching the problems, if we can. And I think they provide some insight into the problems. I try to show you this is the case in some of the discussion before. And our modern earth pressure balancing machines provide, I think, a good procedure to compensate, and simply by controlling the pressures. I think today is a very good protection. You have to be careful in doing that, but I think is good, provided you have a strict control of the machine, and then again a real-time connection between your machine and what you are measuring on the surface. Okay, I would like to thank a number of people here. By the way, Ferrovial also is sponsoring this session. And so these are consultants, and they are also contractors. And then some of my colleagues at UPC for their help, Professor Antonio Ledesma, Alberto Ledesma, sorry, Alessandra Di Mariano, Professor Pérez Roca and Antonio Jens, and Mercedes Ondón, and then certainly to the Spanish Railway Administration that actually invited us to work and to collaborate in this type of work. Thank you very much for your attention. Thank you.
So we are going to open up the floor for questions, but we need to use these microphones so the questions can be recorded. So raise your hand and one of us is going to approach you with the microphone. The microphone is for the recording, so you may need to raise your voice a little bit so everybody can hear your question. So, questions?
I have a very, I mean, I don't understand much how this works, so I'm kind of wondering now with this, the new machines, I mean, where is the design there? I mean, if you can almost basically leave everything to the machine to calculate the pressures, you're measuring how much is the forming, so how much really do we care in terms of what do you calculate if you're just, I mean, everything is now being measured and compensated as you go.
That's right. I mean, these machines have improved very much. I mean, certainly there has been a big improvement in the performance of these machines. But of course, you can make, you should design, you should make your calculations. In my opinion, you should have some green lights or red lights, etc., at the design stage, etc. But later on, it is true that if you have a good team and a good machine and you take care and then you have this relationship in real time of the machine and the measurements, etc., you may achieve really amazing accuracy in your work and then essentially eliminate to a large extent deformations. This is the case today.
Right, it was a very nice talk. I'm curious, you mentioned that with the use of earth pressure balance, now there is a technology and the skills for having zero deformation, zero ground deformation as a result of tunneling. Is that also the case for the slurry shield tunneling?
I don't have experience with the slurry shield tunneling. The only experience is what I read, but not a direct experience. There has been a tendency, at least in the environment that I know, in our country and other countries, is to use the earth pressure balance shield and not to use the other ones because of the complications of the bentonite, circulating everywhere, and then well, the earth pressure balance shield started as machines for a given range of soils, let's say, but they are moving all the time in both directions, in the direction of rock and in the directions of soft soils. We have seen that. So they are more or less universal machines, I think, at present. Tend to be.
Thank you.
Excellent presentation.
Thank you.
One of the things I was going to ask you is, in some of your predictions, you said, well, we didn't do very well because we had to assume something. But if you were to assume something closer to what you measured, how would the results look like? I mean, how much would the volume loss be to essentially get that kind of response? So that was the first.
Yeah.
The first question. And the second question is, in the Sagrada Familia, I presume you didn't have a problem with mixed phase. I mean, most of the problems with tunneling is essentially when you have mixed phase. Do you have any experience with the wall construction with mixed phase?
Yeah, well, I start with the second one, which is the one I remember immediately. But yeah, in Barcelona we had some experience with the mixed phase, and in general the experience was not very good. But the mix was really mixed. Was granite and a almost a deltaic deposit in the low. So this was terrible. But it is true that the builders of this machine they think how to handle this situation, and then they change the way in the design of the head, etc. But in general, the situation is not very good. The machine begins to vibrate, difficult to control, etc. So I think this is, you are right, a complicated situation. This is just a much simpler case. Even if we had this mixture of clays and sands, etc., but this doesn't. It didn't give us much problem. Now the first question is about trying to improve the.
Yeah.
So the modeling, you mean the numerical modeling?
Yeah, you did a numerical prediction based on an assumption of volume loss. So you had to make an assumption of volume loss.
Right.
So now that you have the measurements, is it possible to essentially do a back calculation and say what would have been the volume loss that will cause this measured?
Well, the volume loss later on is measured. So probably if I introduce 0.04%, then everything goes to zero. But to be a little bit more positive in my answer, what we realize is that it is very important to introduce a small strain moduli starting in a very stiff condition, and then this is very important. As soon as you do that, then you get closer and closer to the measurements. This is very nice. So you don't need very complex constitutive models, but as soon as you introduce that, and only that, in a regular elastoplastic with a small strain type of modulus, then things begin to be very close to the measurements.
Well, this is great. You answered the question that I was going to ask.
Yeah.
I was actually going to stir the pot a bit and ask the soil improvement colleagues who are here what their reaction to your comments about the grouting solution were. Rick?
You mean compensation grouting?
I was going to stir the pot, yeah.
Oh, you are asking them, right? Okay.
Best compensation grouting jobs are the ones where you just pre-treat and you don't have to do anything. A lot of the work like Soliton, Shabashi, and UK have done quite a bit of the work over there, and the pre-treating, you're trying to get things tightened up and pre-treated ahead of time, I think is a big deal. The feedback system that they use is really sophisticated in terms of measuring movements and trying to compensate and go back and forth, and as was indicated, the frac and where the frac's going and where the grout's going is not always going in the right place, but in general they've been successful. I mean, it's been successful. I think if the machines can think and do it themselves, there's nothing wrong with that, except we don't get as much work.
I'm not much of an expert with regard to tunnel boring machines, but in the process of that machine transversing through the site, it is applying some shear stresses to the surface of the soil in addition to the normal stresses, is it not?
Well, when you apply a pressure inside the soil, of course, you generate all kind of stresses there.
Right. And so I think that there's some shear deformations taking place in the vicinity of the boring machine that may have relaxed some of the aging effects that have occurred in the soil because of the shear deformations, and that those would take some time to be regained. And I didn't see in your presentation effects of time after the passage of this, and I was just wondering if there are time effects.
Of course, yes. There is. I mentioned something about time effects, but I didn't say almost anything, or nothing. Let me. Yeah, here it is. Here is a kind of an answer to your question. You know these two curves here, one in blue and the other one in this. What is this color? I don't know, magenta. You see they're very close to each other. This one of them is right after the passage of the machine, And this is the last measurement. And this last measurement was made, well, I don't remember, but something like a year or so after the purchase of the machine. So a little bit of change here. But you know, not very clear in what direction. It's so small in this case. But certainly, I mean, in time, you get consolidation effects, etc. But they tend to be small. Now, as a rough idea, these machines, 70% or so of the settlement comes almost immediately as you leave, as the tunnel, the build tunnel leaves the protection of the shield. Then you get 70% or so, even more sometimes. Now, 20% or so, or maybe more, or around that, comes from the initial excavation, from the passage of the machine, etc. And then a little bit later on. And this, and then this, of course, this takes place in time, but is a small amount. Yeah.
You showed the slide that I wanted to see what the distance was between the wall and the foundations of Sagrada Familia. And I was curious, I guess it looks like it's about 8 meters or so. Maybe that's far enough that it wasn't a concern that you might induce movements in the structure with the wall installation?
Of course, there was a lot of concern about that. The first thing we did was to be sure that the pipes were vertical. And this was done very carefully with some technique, which I don't ask me because I don't remember, but somebody came with a very good technique to do that. And the second one, of course, the machine had to be, you know, located very precisely. And I think the machine was at a distance of around, I don't know, 1.5 meters or so, no more, from the wall. Yeah, we didn't have any other possibility. You remember the street was quite narrow, and then, we only had, you know, some small space there to build the. Yeah.
And with your instrumentation, did you find any movement from the wall installation?
For the wall?
Any movement in the structure or in the soil adjacent to the structure associated with the installation of the wall before tunneling?
Oh, okay. That's a good question. I don't know. I don't know. Probably some measurements are available, but I don't know.
Thank you.
What I can tell, which is not an answer to you, but the displacements that are being measured constantly of the settlement of the foundations of the Sagrada Familia, just because of the construction which is going on, are much bigger than the displacements originated by the tunnel.
What kind of soil profiles that compensation grouting works best for? I mean, if we have very soft clays compared to London clay, which ones the compensation grouting will work better? I mean, in terms of excess pore water development and dissipation, or to work for both?
Okay. The better the clay in terms of harder clay works better for compensation grouting. So a clay is much better than sand. This is for sure. But then I don't have so much experience in compensation grouting. I mean, and we tend to avoid that, in fact. But I will say that if you have a hard clay compared with a soft clay, better a hard clay. Just as a, you know, I want to answer, it depends. But I tend to think it is better a hard clay.
And also if we were dewatering along the alignment for some reason.
Dewatering?
Yeah. If we had to dewater along the alignment of the tunnel for some reason, would that increase
you want to compensate the watering effect, you mean?
Yeah. How would it work with if we are dewatering also at the same time as we compensating for the grout? Because it's, you know, we're increasing the effective stress, and we are putting pressure that's, you know, to compensate for whatever, to compensate for effective stress or to settlement. I don't know how to say it. Can we over pressurize with compensation grouting?
I mean, you had the watering, probably you have sands around, okay, a pervious soil, and then if this is the case, you better don't use any compensation grouting.
I mean, sometimes along like a tunnel alignments, right? They're working on a drop shaft at some point where there are some sands there that they need to dewater, and at the same time the tunnel is approaching because it's going to be, you know, a turning shaft or a drop structure or whatever. I mean, sometimes you know, along the alignment you will have more than one activity at the same time.
Yeah.
But the idea is, can we overcompensate?
Well, you can. I mean, theoretically you can do it, but in this case, if you ask me as an engineer, I probably will say, well, you better than use it and then just inject water and raise the water table. I mean, anything except compensation grouting in sand, unless you have a layer of clay in which you can install your boreholes, etc., and then you have more chances of success. You have seen how sensitive it is. You know, because there are many drill holes. I mean, you think it's a good thing to begin to put dozens of horizontal boreholes more or less under the foundation? I mean, I don't like it very much. No.
Yes, I'm a structural engineer. So let me just ask you a question from that perspective. As you were designing the length of that wall, how did that conversation go with the structural engineer? Because you were designing it with the movement in mind, as far as the structure is concerned, right? What was that movement? And then how did you ask the structural engineer, or did you, is this tolerable or not?
Okay, all right. You remember one of my first slides in which you have the Sagrada Familia with, there was some model, there was a model of bars, in fact. We didn't do that, but other people, they did. They made a three-dimensional analysis introducing the soil, the wall, and the Sagrada Familia. And then they made some assumptions, and they said, okay, now 1% of volume loss, and let's see what happened. And then they were calculating the increase in some, stresses in the Sagrada Familia. Well, I don't know exactly what they did, but just to check that nothing will happen. In fact, they knew nothing will happen. So this is the theoretical way to proceed. I mean, this is the rational way, let's say, the rational way. The problem is that there is much more than just rational in terms of structure thinking or in terms of pure geotechnical thinking. I mean, what is behind now is a technology that is there with those machines, etc. You have to understand that, and because why 1%? I mean, because this is the beginning of all this analysis. 0.5%, it turns out that it can be less than 0.1%. So, and then all this analysis is just a waste of time. Yeah, this is the situation. Yeah.
Any other questions? So at dinner we may have the opportunity to ask other questions, maybe not so technical, or maybe.
Yeah, because around the Sagrada Familia there is a long history of stories, very very interesting, social, political, etc.
So I'd like to thank Dr. Alonso again for this fantastic presentation. Thank you so much.